you'll have realised from the stuff that we did in the Enthalpy 1 stuff, all the MC delta T calculations and all of that, that measuring enthalpy changes for reactions is not trivial. Getting accurate numbers, avoiding all those problems with, heat loss and non-standard conditions and the reaction you want not necessarily being the one that happens, all those kind of things can be real nightmare when it comes to practically getting these numbers. But they are important numbers, and we'll see some applications of them in stuff that we do later in the course. So there has to be a way of getting them. But fortunately you don't always have to measure them directly, thanks to an incredibly helpful shortcut which is embodied in Hess's law. So this is what Hess's law says, that delta H, the enthalpy change, is independent of the pathway taken by a reaction, provided initial and final states are the same. So we need to make sure that you are clear what that means. Okay, so here's my high resolution map of the world, and if we think for the moment, instead of about enthalpies, about distances, just as the crow flies distances, we could say, right, I want to know the distance from Winnipesaukee, which is about here somewhere, to Ulaanbaatar, which is about here somewhere, and we could measure the distance, and we find that it's 6,121 miles. Okay, from Winnipesaukee to Ulaanbaatar. But suppose we didn't go there directly. Suppose we decided that, we wanted to, make a stop in Brazil somewhere, and then we go across to West Africa, and then across to India, and then down to Australia, and then up to Siberia, and across to Sweden, and then back to Ulaanbaatar. Then obviously, on this route, going here, and then 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 here, we cover enormously more than 6,121 miles, but at the end we're still 6,121 miles away from Winnipesaukee. And that's kind of what Hess's law is saying about enthalpy, that distance is fixed. No matter how you get there, you can go directly or you can go by some roundabout route, but in the end you still end up the same distance away. And that's how it is with enthalpies. So if we think in terms of an enthalpy profile diagram, which you know about from the previous section, so you might have, if it's an exothermic reaction, reactants here and products here. And you know that delta H, the enthalpy change for that reaction, is this gap here. Okay, so that's what delta H of reaction is. And all Hess's law is saying, well, instead of doing that reaction directly, you could do a series of reactions in which you turn the reactants into something else. Okay, so this would be intermediate stage 1. And then you might turn them into something else and come down here to go into intermediate stage 2. And obviously we could go on, but just because I'm about to run out of board, we'll just complete that and say, right, you could then turn those into the same product. And if you do that sequence of 1, 2, 3 steps, they would each have their delta H's. So this would be delta H1, and this would be delta H2, and this would be delta H3. And you can see it makes sense on that diagram that if you add those 3 delta H's together, they must add up to delta H of reaction, because the enthalpy difference between the reactants and the products is what it is. The fact that you got there by this crazy route instead of going there directly doesn't make any difference. When you add those 3 enthalpy changes together, you get the same answer. So in that context, delta H of reaction equals delta H1 plus delta H2 plus delta H3. That's what Hess's law is all about. And the reason that's so helpful is that delta H of reaction may be difficult to measure, but each of these may be much easier. And so you can measure those, or hopefully, even better, someone may have measured them already and they're out there in the literature, and you can just find the numbers, crunch them together and figure out what delta H of reaction is. And that is what Hess's law is all about. So let's then look at an example of how we can use Hess's law in practice. So this is in fact the example that's in the handout, in the notes. So here the task is to find delta H for this reaction. And this is a case in point where it would be really not impossible perhaps, but very difficult to measure experimentally, because this reaction only happens at very high temperatures. So you need to put in a huge amount of heat, and keeping track of how much extra heat is produced or how much of that heat is taken in, you know, is really quite hard. So if we were able to calculate it indirectly, that would be great. And so you go to a database, and in this case you go to a database of enthalpy changes of formation. Now it's really important that you remember the definitions of enthalpy change of formation and combustion and reaction from the stuff in the earlier part of the section on enthalpy. So enthalpy change of formation, remember, means that it's the enthalpy change for formation of 1 mole of the compound from its elements in their standard states. So in the case of calcium carbonate, that would mean calcium metal and carbon in the form of graphite solid and oxygen gas. So formation of 1 mole of a compound from its elements. And it must be from its elements, not just from whatever you feel like forming it from. Obviously, if you form it from different things, then delta H would be the same. So you need to know that definition. And so those numbers are available. Who knows how they were measured? Doesn't matter. They've been measured, so we can use them. So how does Hess's law work? Well, the way it works is that you think, right, we've got these numbers which connect these 3 compounds to the elements they're made out of. So what we can do is set up what we tend to call a Hess's law cycle, in which we put the elements at the bottom. Now we could actually write in what they are, so we could put calcium solid plus carbon solid plus 1.5 O2 gas, and that would be fine. But actually, as we'll see, it's not really necessary, because the details of what the elements are doesn't figure in the calculation that we're going to make. So although that would be perfectly fine, generally speaking, unless you're asked to put it in, you can just leave it out and just write the word elements at the bottom, so that we're clear what we're talking about here. And then we can put these numbers onto the diagram. So we're following the definition. It's formation of the compound from the elements. So in other words, we have arrows going up here from the elements to form the compounds. So don't guess which way the arrows go. When people go wrong in these questions, it's usually because they get arrows in the wrong direction. But if you stop and think about what the definition is, then you don't do that, because you just think, oh yeah, it's forming the compound from the elements. The elements turn into the compound. Okay, so there shouldn't be any doubt which way the arrows go. And we can just label that arrow and say, right, if we do that, take that set of elements and turn them into calcium carbonate, it's minus 1,207 kilojoules per mole. Now if we take the same set of atoms, because this equation across the top is balanced, the same set of atoms down here could either turn into that or turn into that. Because, by definition, if this is a balanced equation, you need the same set of elements to make these or to make those. So we can put another arrow up here leading up to these products over here. And I just tend to lump them together like that. Some people draw separate arrows for each one. It really doesn't matter. The method is the same. But I just do it like this just because it's lazy, I guess. Okay, so what do? Well, we say, right, if we're making a mole of calcium oxide, that's minus 635 kilojoules per mole. And we're making a mole of CO2, so that's minus 394 kilojoules per mole. And if we add those together, we get minus 1029 kilojoules per mole altogether for taking the elements and turning them into those compounds. Now why are we bothering to do this? Well, because if we now invoke Hess's law, what he says is that this is the reaction we're interested in, but we can do it by an indirect route, because the total enthalpy change is independent of the route taken. So we can make this change in 2 steps. We can come down to here, and we can come back up to there. And we can easily find the numbers for this step and this step from the ones that we've already got. Add them together and we get our answer. And that's why Hess's law is so powerful. So if we look at that, the first leg is the opposite of that one. So this is the elements being turned into calcium carbonate. We're doing the opposite. Now again, if you think about the enthalpy profile diagram for this process going from the elements to calcium carbonate, you can see it's exothermic for forming the compound. So if the elements are here, here is calcium carbonate, and we're saying that making that change is -1207. And it's sort of obvious on the diagram because, you know, this is just an axis on here. These would be numbers up here. If you like, we could set this at 0 and this would be -1207. Okay, so it's a numerical scale up here, and it's then fairly obvious that if that's -1207, then that is just +1207, because it's the same gap size, but just going in the opposite direction. So you don't need to draw that out, but that's just to convince you that what we're going to do next isn't cheating, that if we just have the same transition but going in the opposite direction, all we do is change the sign. So that's +1207 going that way. So that's the first leg of the journey. The second leg takes you from here, from the element up to here, and we already know what that is because that arrow is exactly the same as this one. So that's -1029 going that way. So now we're almost there, because we can just combine those numbers and get the delta H of reaction. The reaction across the top is that leg plus that leg. So it's +1207 -1029, which works out as +178 kilojoules per mole for that reaction. So that may not seem completely trivial to you if it's the first one you've done, but hopefully you can appreciate that that's enormously easier than actually doing the experiment and figuring out what delta H would be directly. So this is a really, really powerful tool. Now these cycles are the key to it. And what tends to happen is that as people get more confident, they decide they don't need to bother drawing the cycles out, and they just kind of visualize it in their head, and that's when numbers get messed up. So let me urge you right from the beginning to think it's always worth drawing that cycle out, because first of all, you're much less likely to make mistakes if you do it, and secondly, because if you do make mistakes, it's much easier for people to see what you've done wrong and therefore give you credit for the bits you've done right. You know, if you've just made a simple slip up along the way. Let's then look at a more complicated example. So this reaction is called a Fischer-Tropsch reaction, and reactions like this have been used in the past to make alkane fuels from carbon monoxide that comes from coal and hydrogen. So it has some industrial importance. Now measuring delta H for that particular Fischer-Tropsch reaction would be essentially impossible as a direct thing, because, as you can imagine, if you're going to make alkanes by reacting hydrogen with carbon monoxide, you're not just going to get C10H22, you're going to get a whole range of alkanes with different numbers of carbons in there, and trying to choose conditions where you would only get one would essentially be impossible. So that's a number you could not measure directly, but you can calculate what it would be using Hess's law. So again, we've got the necessary enthalpy changes of formation, which are easily available numbers that people have already measured. So that's what we're going to use. And as soon as we see that that's what the numbers are, and that's the key thing in Hess's law calculation, is to be really clear what these numbers are that they're giving you to play with. So as soon as you see that you have enthalpy changes of formation, you think, right, I know what to do with those, and that is set up a cycle in which the intermediate state, the one that forms the link between here and there, is going to be the elements. Okay, but you only do that if you're confident that the data you're using are enthalpy changes of formation. If there are other kinds of enthalpies, you may still be able to use Hess's law, but it won't be in the same way. So let's do the same as before and say, right, we know that formation means that you go from the elements to form either these compounds or these ones. So the enthalpies of formation will be either taking us up to the stuff on that side or up to the stuff on that side. So what have we got here? You look at hydrogen and think, oh, that's not on the list, so what are we going to do about that? But of course, the reason it's not on the list is that it's still an element. You've got elements here, so that would be H2, and it's still H2 there, so it doesn't have an enthalpy change of formation, or if you like, it's zero, because it's not changing in any way. So that's quite common in these problems, and the thing to do is just realise, yeah, that makes sense, that that element isn't changing in that step, therefore it has no contribution to the enthalpy change. But the carbon monoxide is. So carbon monoxide, the delta H of formation is minus 111 kilojoules per mole. But the key thing is that in this equation we require 10 moles of carbon monoxide, not just one. So that means that the total enthalpy change for making those 10 moles of carbon monoxide will be minus 111 times 10, okay, which is minus 1110 kilojoules per mole. Going up that way. If we take that same set of elements and turn them into these things instead, then we're making 1 mole of decane, so that's minus 249. But we're making 10 moles of water, so it's minus 242 for 1 mole, but we're making 10 moles, so it's minus 242 times 10. Okay, so again, taking account of the balancing numbers like that is absolutely crucial in these Hess's law calculations. If you don't do that, you're obviously just going to get meaningless numbers. And hopefully you can see that that makes sense, because these numbers are kilojoules per mole, the enthalpy change for making 1 mole of that compound, but the equation here requires 10 moles of that compound. So we can add those numbers up, and if we do that we get minus 2669, whoops, 2669 on that side. Okay, so now we've got all the numbers we need, and so now we invoke Hess's law again. And we say, right, this is the delta H that we want. Okay, that's our mission, to find that number. And so we invent a pathway which goes first down there and then up there. Okay, because the sum of those two steps, this one followed by that one, has the same overall result as that. And Hess says if you add together the enthalpies for those two steps, they'll add up to the same number. That's all we're doing here. So the first of those legs, you can see it's the opposite of that one. So it's minus 1110 going up that way, so it's plus 1110 going this way. Second leg of the journey is exactly the same as that one, because the arrows are going the same way, and therefore the sign doesn't change. So it's minus 2669 going that way. And now we're almost there, because again we can just add up those two individual delta H's and they'll add up to that one. So delta H of reaction, which is what we set out to calculate, is equal to plus 1110 minus 2669, which is minus 1559 kilojoules per mole. Okay, we'll look at one more example of using enthalpies of formation, and this one is a little bit different again, because this time you can see that we've been told what the overall enthalpy change of reaction is, so somehow someone has managed to measure that. And we've also been told what the enthalpy change of formation of NO is, Hydrogen, of course, we don't have to worry about, because as we know, if it's an element, it's going to be unchanged, so its enthalpy of formation, if you like, is 0. And we've got the number for steam, which is over there, but we haven't got this one. And so the mission this time is different. It's to take the numbers we have got and solve for that one, the enthalpy change of formation of N2O. So you need to be able to do problems this way round as well. So let's see how to do that. So again, the first thing is double check that we are using the right kind of data. Enthalpy change of formation means that we can set up a cycle in which the link across the overall reaction is the elements. And again, we remember that formation means that you start with the elements and they turn into the compounds. So we have arrows going up there and up there from the elements to form the compounds. Let's put the numbers on those. So we're making 2 moles of NO. So enthalpy change of formation of NO is plus 90. So it's plus 90 times 2, because we've got 2 moles. And hydrogen, as we said, is 0. So no contribution from that. So that gives us plus 180 going up that way. If we come up here, we're making N2O and steam. And steam, we've got the number 4, there's just 1 mole of that, so that's minus 242. And this one, what we're going to do is call it X. Okay, so we're going to say minus 242 plus X. And when you do that, you should always make a note of what X means. So we're defining X to mean the enthalpy change of formation of N2O. Okay, and you can see that's what that corresponds to, because it's going from the elements to form an N2O molecule. So that's X there. So then we can invoke Hess's law and say, right, that overall change is given by the sum of this leg and that leg. So this one is the opposite of that one, okay, because it's the same gap but going the opposite direction, so we change the sign. So that's minus 180. This one is exactly the same as that one because we're going the same way, so we don't change the sign. So that's minus 242 plus X going that way. Okay, so now we can write a statement of Hess's law which says that that number is equal to the sum of those two. So we get that minus 339, which is the sum, is equal to minus 180 minus 242 plus X. Okay, so we can then rearrange that to get X and get that minus 339 plus 180 plus 242 is equal to X. And if we work that out, we get that X is equal to plus 83 kilojoules per mole. Okay, so it's just a matter of writing down that statement with that little bit of algebra in there for X to substitute as the unknown number, and then just rearranging. So we've got to move those two terms over to there, so we add 180 and 242 to each side, so they arrive over there and disappear on the right. And we can then easily solve for X. So that's our answer, that the delta H of formation is equal to plus 83 kilojoules per mole. Okay, so that's going to be another important string to your bow, is developing the confidence to use X algebraically like that to solve for an unknown number by just saying, right, if we know what the answer is, we can write that on one side and say that's equal to that plus that, build the X in, rearrange, and you get your answer. The other thing that's worth commenting on in relation to this example is that the answer was a positive delta H, and so indeed was the enthalpy change of formation of NO, and that's fine. Delta H of formation can be either positive or negative. It just depends on what the compound is that you're forming. So don't be alarmed if you get a positive number. That's fine, because it just depends on the relative strength of the bonds in the elements, the ones that you have to break, compared to the bonds in the compound that you're forming. So if you have to put more energy in to break the existing bonds in the elements than you get back out by forming the new bonds in the compound, then it will be endothermic, which was the case for NO and indeed for N2O here. So don't have expectations about the sign of delta H of formation, because it can be either way.